So welcome everyone. Yeah, I'm happy to present Oxara, the technology we use, the products that we developed so far, and projects that we were working on. And as already introduced, my name is Letizia Caderas, and I studied civil engineering at ETH with a focus on building materials. And right after the studies, I started working at Oxara, and I work for 4.5 years now at Oxara. And yes, there at Oxara, I work in the material development. That's my field of work. And then, so Oxara was founded in 2019 by Nyandi Londru and Thibaut Demolin on the right picture. The spin-off was founded based on the research findings that Nyandi found during his PhD at the chair of sustainable construction materials here at ETH. And since 2019, we have grown and we are about 14 people, and it's a mix of material scientists, chemists, engineers, architects, and people from the business side. And the mission of Oxara and our goal is to reuse the waste from the construction industry in low carbon footprint building materials. And the two main waste streams that we are addressing is the clay-based excavation waste and the construction and demolition waste. And here I want to directly name a few numbers to see the importance of these wastes. So based on data from 2022 in the canton of Zurich, there were 3.5 million cubic meters of excavation waste produced. And of these 3.5 million cubic meters, around 65% are used to refill gravel pits or raw material quarries. So basically it means that you use this material to fill holes that you were digging for sourcing the raw materials. Another 5% are landfilled in the canton of Zurich, and 21% leave the system boundaries of canton of Zurich, and that basically means that it gets landfilled in another canton. And then about 9% are reused directly in the construction. So here the reuse quote is actually pretty low as a building material. On the other hand, so compared to the 3.5 million cubic meters of the excavation waste, we have around 1 million cubic meters of the demolition waste that gets produced each year in the canton of Zurich. And there around 90% are reused in the construction, and a really big part of it is reused as recycled aggregates. And as a comparison from data from 2018 for the whole Switzerland, it's around 60% across whole Switzerland that is reused as recycled aggregates. And the rest of it is either landfilled or also leaves that system boundary of the canton of Zurich. So it means that these waste streams that we have each year, they are huge, and we need to propose good solutions for these wastes. And Oxara wants to do it by developing admixtures and binders to be able to reuse these materials. And so for your understanding, Oxara is basically like the, I hope I'm still online. Yes. There was a, okay, so it means Oxara is like the admixture and binder producer, and not the producer of the final building material. So the building material, the poured earth, is then produced by a material producer like a kebab, and we are producing in an analogy, the cement like Holcim or the admixtures like Sika. This is our role in this. Yes. In this industry. And so schematically shown, it can be explained like this, that for all our building products that we develop, we have water and sand and gravel that we are using. And then for the excavation waste, we use the earth plus some admixture at a low dosage as the binder. And for the demolition waste, we use the demolition waste in a milled form together with some activator as the binder to produce the earth-based and the demolition-based products. And first of all, I want to start with the earth and with some general explanations and how we want to use it. And really, before I start with the Oxara specific informations, I want to make a small turn on some other general earth-based informations that we think are important. So what is earth? I think you heard today, but also maybe for the people online joining, earth, as it is referred to in English, or Lehm in German for the Lehmbau, it's the mineral mix of different grain sizes. So if you cut into the ground and you look at the sections, the first layers are organic matter that are not used for the earthen construction. And then if you dig deeper, you come to the mineral layers, and these mineral layers are composed of different grain sizes. And from small to big, there are the clays, and the clays are really tiny. It's about 2 micrometers in size. Then you have the silt, sand, and gravel. And it's a bit definition dependent on where you draw the line of what is lehm, but one can say it's basically the silt, sand, and gravel. But the most important ingredient are the clay particles. And on the left side, you can see a microscopic image. And you can really imagine this, or as you can see, these clays are platelets, and these are silicate layers. And these silicate layers, they are the binder of the earth-based materials. And these silicate layers, or these clay platelets, they have a strong interaction with the water. So they can actually surround the water molecules around. And these interactions, is quite decisive or important for the properties to follow. And to understand the Earth's material, it's, I think, very helpful to have this picture in mind, that in your earthen materials, you have the different grain sizes. And then you can imagine that you have the sand grains, and around these sand grains, you have the clay platelets that are oriented as the matrix around. And then if you zoom in even to these clay platelets, you find in between the clay platelets the water that is in the very small pores as capillary bridges. And it's actually these capillary bridges that give the cohesion of the clay-based building materials. And it is also this water-clay interaction, and also this principle that is defining for 4 aspects that I want to point out on the earthen building materials. So first of all, on this clay-water interaction that is important, it's the drying. So when you want to build with earth, in very general, you need to add water to the clay to make it workable to whatever consistency. And once you place your material, it needs to dry. And that drying it's really a drying. So all the water needs to evaporate, unlike in cementitious systems, for instance, where the water gets bound by a chemical reaction. Here, everything that needs to go out needs to evaporate. And that takes time because it goes over the surfaces. And it's important to keep in mind that if you, for instance, double the size of your wall, you don't double the drying time. It increases exponentially, as this is not a linear process. So drying times in earthen constructions take time. And then along with the drying comes the shrinkage. So you have the water around these clay particles. And first, maybe the clay particles, they don't touch each other because they're separated by the water. And then once the water starts to dry and to evaporate, it leaves the system, and that leads to a volume change. And that volume change can be quite drastic, as you can see here in this video, where you can see how a clay cylinder shrinks. I can play it maybe one more time. And this is, of course, a very extreme case when you have only clays and not sand and not gravel, which reduce the shrinkage. But yeah, earthen materials have shrinkage. And this is because if the water withdraws, also these capillary bridges pull the material together. And it's important to keep it in mind for earthen construction. And then the second aspect is how it's like the compressive behavior or of the earth-based materials. I think you might have heard that earthen construction materials should be used as compressive load-bearing materials. They are very weak in tension or in bending, and this is also due to how they get their cohesion. And it's important to know that the compressive strength is dependent on the moisture content of the material or on the relative humidity that you have in your room. So on this figure, on the x-axis, you have the relative humidity inside the room or outside, and on the y-axis, you have the normalized compressive strength. And if we take the compressive strength at 50% relative humidity, so on the left side of the figure as 1 in a normalized strength, you can see how the strength decreases with increasing moisture. And the reason is that the clay or the clay-based the construction material can absorb the moisture, so it gets adsorbed around these clay particles. But if you have this water adsorbed around the clay particles, it also means that you weaken these capillary bridges that I was showing in the beginning. So you lose the strength when it gets more moist. And this is a kind of a drawback of earth-based materials, but on the other hand, if you look at it from a different perspective, it is also an advantage, and that is that the clay has really the capacity to take up a lot of moisture. And this is a graph which shows different plasters, and you can see that the clay plaster has a very high capacity to take up moisture and then at a later stage release it back into a room. So clay is an excellent moisture buffer compared to other plasters like the cementitious one that pretty fast is saturated and then it cannot take up any more moisture. And also concerning some building physics properties that we would like to point out, it's the density of the massive clay-based construction materials can be assumed around 2,000 kilograms per cubic meters. Clay itself has a high thermal capacity due to its mass, but it also has a high thermal conductivity. So a massive clay is a bad insulator. Clay in a massive construction technique can give good sound insulation and it's non-flammable. So it is concerning the building physics properties. Yes?
I think slides before, right, like high thermal capacity and so on. I mean, I think these are linked to some depth of the wall. I mean, you cannot have like a very slight wall and then you don't have a very high thermal capacity. All these are linked to some, you know what I mean?
I know what you mean. So maybe to, yes, of course, it is linked to the thickness that you bring. If you only have like a 2 centimeters clay plaster, you don't bring a lot of mass. But it's the point that the particles of the clay itself have a high density, around 2.7. And these, if you have them well compacted, and then if you use them, you can bring a lot of mass into the building. So compared to some other materials which don't even have that basis, you can use clay in that way.
I mean, it would be interesting to know when we can say that a wall can have this high thermal capacity and from which point.
Yeah.
Yes, so that we understand what does it mean to build a compact wall or just.
We can maybe get back to it at a later stage. And then the fourth aspect, which is, I think, related to this clay-water interaction, is the durability. It's again that the clay platelets, they are not bound, they're held together by the water, but it also means that if you introduce more water, the clay material is not stable. So the earth-based construction materials, they erode when they're exposed to rain, and they are not water resistant. And here is a picture of the Vogelwarte Sempach, where you have one facade part which was exposed to the rain, and another one was protected by the rain, from the rain, because there was a balcony. And as you can see, the difference is big, and I think this is also something to keep in mind as a general aspect for earthen construction materials. So to summarize on the earthen construction materials, we have the following advantages. From the building physics property side, you can use the clay-based building materials to introduce a thermal mass into your building. You can use it as a moisture buffer if you use it in the interior, and it can give some fire resistance, also protecting other building materials. The advantages on the environmental side is that it has a low CO2 footprint. You reuse this excavation material, which is currently more or less a dumped material, and you can source it in principle quite locally as it is widely available. And also for design, I think the options on how to use it design-wise are broad. But then, of course, the question arises a bit, okay, it has advantages, it's widely available, but why is earthen construction not more used? And I think there are many reasons, and one of them that we want to tackle is a bit of processing. Some vernacular construction techniques, they use a lot of human power, and they need a bit of more of effort, and Oxara is looking into this easy processing. So the idea is to make the earth pourable, and then if it's pourable, you can use the same infrastructure as it is already widely available as for concrete, conventional concrete. And the advantages would be a faster processing, a reduction of the labor time, yes. But with maintaining the clay-based material properties. So this is the idea, and how does it work? The idea or the admixture technology behind is that if you have clay and you mix it with water, a certain amount of water, you can maybe reach a state as it is on the left side of the picture in a plastic state. And of course, you could reach the state on the right-hand side by adding just more water, but you actually don't want to use that much more water, because if you add just more water to reach a fluidity, you also have a much higher shrinkage and you introduce too much water. And also then later it cracks and loses its strength. So the idea is to do that change from plastic to liquid with an admixture and not by adding water. And the way how that can work is that, now going back to these clay platelets, they have a surface charge. And on the edges, they are charged positively, and on the sides, negatively. And then in a normal state, you have the positive charges, which are attracted by the negatives, and the clay platelets arrange in a card house structure. And in this way, they can also have a lot of water in between. And then if you introduce a dispersant, so this is an admixture that can change the surface charges on the edge from positive to negative, then the edges get repelled and they disperse. And if they're oriented in this parallel way, they can much more easily slide past each other. And then you can have a higher fluidity with the same amount of water. And that's the principle of the admixtures we are using. And then if you want to stop the fluidity because you placed your material, you want to reverse that effect, and you do that by adding a coagulant that then consumes the dispersant. And here we have a lab demonstration on how this works. So first you mix the dry earth with a certain amount of water, and then you mix. And then with this amount of water that we put, it's not fluid, because it was not enough water. And then you add the dispersant and you can mix it in. And then you can see that you can get a very well flowable paste that is also suitable for processing on a construction site. And then you add a coagulant. And here in this video, for demonstration purposes, we take a coagulant that reacts really fast. As you can see now, it already starts to stiffen. But of course, in the construction site, you don't want to have such a fast reaction. And also, it's not a possibility to add this coagulant after you place the material. So everything needs to be added in the beginning when you mix the material, but that means that you need to choose a coagulant which reacts rather slow so that you have enough time to process the material. Good. And then here you can see in this video how that looks in an industrial scale. And then the material can be processed, as I said, with the conventional concrete infrastructure, and it can also be pumped, as you can see on the right-hand side on top. So this is the basics of our technology that we use for the clay-based construction materials. And of course, when speaking of admixtures, very soon the question arises of when is it still unstabilized, the earth, and when is it stabilized? And I think it's a very important discussion to have. And also for each project, you should consider carefully what is more suitable. That's why I want to quickly dive into the topic of unstabilized and stabilized. So the way we see it, for us, the unstabilized earth is an earth that is not water resistant. It's still soluble in water, and it dissolves, as its strength mechanism is only the drying. So if it only dries and gets its strength, then it also means that if it's in water, it dissolves. And this is unstabilized earth. If you introduce a reactant or a chemical that consumes water and reacts with the water, and it binds the water, and then it also binds the clay platelets in more or less, depending on the dosage that you stabilize, then you can put it into the water and it will not dissolve anymore. And then often at the first look, one could say, okay, it's very practical to stabilize the earth, because then you avoid all these challenges like its dependence on the moisture content from the strength, or that you don't need to take so much care on the durability. But of course, it's not that easy. And yeah, I think the careful evaluation should consider the following points. So for unstabilized earth, as I said, it dissolves in water, and the stabilized doesn't. And this is because the source of strength is, on the one hand side, purely the drying, and for the stabilized one, it's the drying plus a chemical reaction. And because this chemical reaction takes place that binds the water and also binds the clay particles together, the strength development is accelerated. So Unstabilized earth has a rather slow strength development. It also depends on when you remove some formwork or how dry it is, how fast it can dry. And for the stabilized one, you have some reaction taking place, which gives you like a bit of a boost. And then if you look at the dry strength or the end strength of the material, that story is not that clear anymore. What's better, if unstabilized or stabilized? In general, we say that poured earth has a compressive strength between 2 to 3 megapascal if it's unstabilized. And if it's stabilized, it can happen that if you use a low stabilizer dosage, you first actually disturb that clay matrix, and then you lose the strength, and you need to dose at a high dosage to increase the strength higher to the one compared when it's unstabilized, because you first disrupt this clay network when you introduce a stabilizer. So it's, in general, one could say, not the most efficient if you use the stabilization only because you want to have a high end strength, because then you often go into high stabilization dosages. And then on the moisture buffering side, the unstabilized one performs better. This is clear because you have purely the water and the clays which can interact with each other. And if you introduce a stabilizer, this also binds the water and interferes with this interaction with the water. The same for the recyclability, and for the recyclability, it's a bit more drastic. So if you have unstabilized clay, you can dissolve it in water, and that makes it reusable infinitely. If you add a few like admixtures, it's a bit of an in-between case. You have an accumulation of these admixtures, but if it's still dissolvable, you can reuse in the same way as you do it with pure raw earth. But if you have the stabilized clay and it binds together, then you don't have that easy way of recycling because it doesn't dissolve anymore. That's a drawback. And then on the environmental impact, clearly the unstabilized one has the lower CO2 footprint. And for the stabilized one, it really depends on the stabilizer that you use and the dosage that you use. And for the end of life scenario, if you have a raw earth or one with a very low percentage of admixture, it is landfill A. So if it's unstabilized, and if you stabilize it, then it counts as this construction material, which needs to go to landfill B. Good, and having this said, now we go back to the Oxara earthen product. As a reminder, the way we use it, we have the water, we use the clay and the admixture as the binder, add sand and gravel, and from this we have 3 different building products. We have 2 poured earths. There is the Oxara Care, which is the unstabilized poured earth, and the Oxara Nosim, which is a stabilized poured earth. And then we also produce a stabilizer for compressed earth blocks. Yes, and then, of course, there's the question how to use this material now that we have this product, how to apply them in a building. And we recommend to be able to benefit from the moisture buffer capacity of these clay-based building materials, and also because the durability is limited when it's exposed to rain, the interior use for earthen materials is suitable. And in the interior use, we recommend either non-load bearing or very low load bearing walls or screeds. Or what's also very suitable are hybrid elements where you can benefit, for instance, together with the wood, that the wood can do the structural part, and then the clay and the massive earthen construction material can give the thermal mass and take the moisture buffering. So these are the 3 main applications for earthen materials that we see. And now I want to present a few project examples. The first project example is there were 2 houses built in Vandœuvre, a garage and a pool house. It's a 1-story building. The walls are not load bearing. This was done with stabilized poured earth because as the client and the contractors chose to build with it. What's special here is that, I don't know if you can recognize it very well, it's like the detail of the walls that you can still see from the formworks, that you can see the texture of the wood. And this is only possible because the poured earth is in such a liquid state that it can actually adapt to the structure. And if you might have noticed, I just said that we recommend the interior use, but I think it's also a reality that a lot of people, if they use earth, they want to display the earth and also want to display it towards the outside. And then it's very important that you use a good hat and shoes, as it is done here. So the roof needs to protect the walls from the rain, and the concrete part in the bottom needs to protect the earthen wall from the capillary rise from the ground. And here, quickly, the technical specifications summarize. We recommend for this poured earth wall a thickness larger than 25 centimeters, and really a maximum height of this 4.5 meters, because if you go higher, it really gets tricky to demold the walls. If you would have a prefabricated process, maybe it's a different story, but if you want to demold, you need to have enough strength to be able to take away the formwork. And if you don't want to overstabilize, there is a limit in height. And you need to plan dilatation joints, we say every 4 meters, to avoid the shrinkage cracks. Also on the environment, so how it looks like on the environmental impact, we compare it to a calcium silicate block wall of 18 centimeters. And if you compare the Nossim wall to this block wall, you have a reduction potential of 40% in CO2 equivalent. So I go on to the next application and the project example. So here you can see the first residential floor that we built in Ackersteinstraße in Hönk in Zurich. Exactly. So for this project, it was a concrete slab, then some cork insulation, and the 8 centimeter thick floor that was casted on top. It was cast in situ by pumping, and then it was let to dry. The floor cracks, the cracks were filled by an earthen mortar, and then they made a terrazzo finish. This means they grinded and polished it as it is known for a terrazzo. Yes, and for the floors, we have the following recommendations. So earthen material can be used, or poured earth can be used for screeds or terrazzo floors. If you do so only for residential areas, because for public areas, the point loads are too high and also the possible abrasion that can happen. You need to look for a suitable surface treatment where we currently recommend some Wasserglas, so sodium silicate, and some stone oil that we are using, but this is a bit of still I think a bit of a trial and error, also where it's most suitable given the project or where the client think they are confident enough to use whatever surface treatment you propose. And from it's compatible with floor heating. A floor heating can actually be beneficial for earthen floors, as you can speed up the drying process when you start to heat. And for the section on how to build, it's important that between the earthen layer and the insulation, the sound insulation, which is rather soft, that you have like a load distribution plate. Because you need to be able, as the earth is soft as well, you need to be able to distribute the point loads and that you don't get too much bending caused by the acoustic insulation. And if we compare the Nossim screed of 8 centimeters to a cement screed of 8 centimeters, there's a saving potential of around 45%. But as this is a stabilized floor that we are presenting, it's also not easy to say one number. It also, again, depends on the stabilization dosage that you were using. Of the screeds, we recommend 8 centimeters. With other conventional building materials, of course, you can go lower, but as the earthen material does not comply with the norm for screeds, we recommend higher thicknesses so you don't get problems with bending. Yes. And then, yes, another project that I want to do as a representative for a earth-based / hybrid project that we did is a timber earth slab at Altichesi in Rotkreuz. It's an old cheesery where they built in a hybrid earth wood ceiling, and the ceiling was cast in situ as it was not possible to bring into the building some prefabricated elements. Yes, that's about it, what I can say here. And again, so for the hybrid end elements in general, it doesn't need to be a ceiling, but one can say that in combination with the wood, the two materials can profit from each other. So the wood can take the structural part, and the clay-based materials bring the mass and the moisture buffer and maybe some acoustic insulation. Yeah, you can see the dimensions that were used in this project, and concerning the environmental footprint, we don't have numbers to present which compare this building system to another slab, So what we can present is that we present the cubic meter CO2 footprint if you would use it as a filling material, and if you compare conventional concrete as a filling material to the poured earth or the rammed earth, you have big saving potentials up to 80%. And then the last project on the earth-based side that I want to present is the blocks. These blocks are used in a residential building in the canton of Zurich. They serve as a good sound insulation and as separation walls. And in this project, also a clay-based mortar was used to mason the stones together. And the blocks are produced by TerraBlock, and they are available in the following dimensions that you see. You can either use a clay-based mortar or a conventional mortar. With the clay-based mortar, the tricky thing is that it's not that commercially available in the project. So you need, if you want to use it, you need to have a supplier or a source where to get it. It's not that you can just buy it, or it's harder to get, let's say it like this. And another thing I want to mention is for the blocks, there is the SCR norm 266, which has declared masonry in it. And this declared masonry does not specify the material the masonry needs to be made of, but it defines material properties. And the stones and the mortars comply with this norm, so you can build with the norm of the declared masonry. And if we compare the Oxara blocks to fired clay bricks, you have a saving potential up to 50%. Good. So, and then the outlook on the earthen material from our startup side is that we are continuing doing research. Once in the InnoSwiss flagship Think Earth, there we are in a sub-project where we are researching a robust earth mixes and trying to make a step towards the industrialization of the earthen materials, and also to test large-scale earthen building elements like walls or bigger masonry wall to study the scale effect of the earthen building materials. And then we are also engaged in timber earth slab project with the TU of München. There it's the research on producing a hybrid ceiling element, and internally we are developing a liquid soil. And the liquid soil is used to fill the trenches and to surround the pipes and protect the pipes. And our goal is to do that without cement. And that was now the earthen side, and then we'll jump to the demolition waste-based side, where again we use it as a milled material. But first of all, what is demolition waste and how is it used nowadays in Switzerland? So demolition waste, it's the mixed composition of bricks, concrete, natural stones, and some other mineral construction materials that are present in a building. And there is a distinction between the concrete waste, which is the pure concrete waste, and the mixed demolition waste. And it's produced in that sense in the following way. If a building gets demolished, you first demolish the upper floors, and very often these upper floors are not separated. So the bricks, for instance, the masonry is not separated from the concrete, and that generates that mixed demolition waste. And the reason why it's not separated, there are two reasons. First of all, it's too expensive to separate it. And on the other hand is that if you would just take the concrete waste out, you, in the sense, you lose the quality a bit for recycled aggregates. So you actually want to have a certain fraction of concrete aggregates or concrete demolition waste inside your mixed demolition waste, because that increases the quality for the recycled aggregates. And then if the building is the floors below ground are demolished, that's the point where often you have some pure concrete waste, because there the floors below the ground are very often built in pure concrete. And also so you can see also this composition of the demolition waste can vary quite a bit. It's very heterogeneous, and it also depends on what building you demolish, from in which year it was built, because either it has a higher percentage of masonry or a lower one. And the reuse possibilities nowadays, there are 4 of them. There are 3 ways to use it as recycled aggregates, the demolition waste. You can use the recycled granulates either in a loose form, so you don't bind them with a binder, but in that loose form, one has to say that the leaching of salts is critical. So it cannot be used at a place where water can flow through the loose aggregates. So if you have the loose aggregates and water can flow through, salts could wash out, and that is not allowed by the regulation. Another form to use these recycled granulates is to use it in a lean concrete, in German Magobeton. There, the mixed demolition waste is bound usually by cement. And the third option would be to use this recycled granulates in the structural concrete. But that is in bracket because it is not very often done, because due to this heterogeneity and a very high fine fraction of this demolition waste, it is very tricky to use it in a structural concrete. And only few producers of these recycled granulates are actually capable of treating them in a way that they get the quality to be used in structural concrete. And then the fourth option is to not use it as recycled granulates, but to use it as a raw material in the cement production. And if it's used in the cement production, it is milled. And an example for this is the Susteno cement, for example. So now I'm going to show, illustrating again how Oxara is using it. We are milling the demolition waste and combine it with some activator, and then we have the water and this binder of milled demolition waste, where the demolition waste accounts up to 50% or around, and then we add sand and gravel and have also a concrete-like material, but with a cement-free binder. And we are following this strategy because we see the need that one needs to propose a solution for also the fine fractions of the recycled granulates, or more that these particle sizes can vary a lot. And so by milling, one can at least control this heterogeneity. And that we want to take the approach to use it in the milled form. The advantages of using the demolition waste in the construction materials are, let's say, obvious. You reduce the CO2 impact of your binder that you create. And that means also you conserve natural resources by reusing the demolition waste, and you save landfill space. So for your idea, like I said, if you use 1 ton of that binder, you can save up to 400 to 600 kilograms that would otherwise go to the landfill. And there is a little illustration in the video on how it's cast. So if you see it from the outside, it's really similar to a concrete and to be used similarly. Good, and now I want to give you an overview of the technical specifications of that cement-free binders. The technical specifications to that belong to exposure class. So for what can you use that binder, for which kind of concrete to use it afterwards, in which application, and the exposition classes is basically a X0, so it should not be critically exposed to either freezing and thawing or to carbonation. I don't know, quickly, carbonation, it's when you have a cementitious concrete, the cementitious concrete has a very high pH, so it's alkaline, and that high pH protects the reinforcement bars in the concrete. So for cementitious concrete, you have a protection from corrosion by the high pH of the concrete. And carbonation means that if the CO2 from the air ingresses the concrete, the CO2 reacts, and that reaction decreases the pH. So you want to make sure that of your concrete, the pH is staying at a high level so that your reinforcement bars are protected from corrosion. So one is actually for binders, one is measuring the carbonation resistance, meaning how fast they carbonate, how fast they lose their pH. And in our case, the ULEZ binder has a lower pH and it does not comply with these carbonation limits that are given to use it in, where carbonation limits are given. That means that if you use a reinforced ULEZ, currently you have to use it in applications where the corrosion is not happening because there is no moisture. So there are always 2 ways to protect the reinforcement bars. Either you have this pH or you use it in an interior wall where anyway the steel reinforcement bars would not corrode. And also for the freeze-thaw resistance, we don't achieve the limits that are given. So the freeze-thaw resistance class is F1. And in terms of strength, you could see a strength development curve here. The orange curve is the ULEZ binder, and the other one is a cement 32.5 of that strength class. And the main difference is that in the early age strength phase, so in the early days, the strength development of our binder that we are currently developing is lower. So that can elongate the demolding times that you have for your walls. Exactly. And then the environmental impact, if you compare it to SM1, the ULEZ saves up to 60% of the CO2 footprint. So to summarize, for this new binder, as it is also actually a bit often with alternative binders, you need to be careful with the exposures that you use it, because it cannot fulfill the carbonation limits. And in this case, we have the limited early age strength development. And with that in mind, based on our current development state, we are working on the following applications and propose the following ones: the lean concrete, the screeds, and the pavers. And the reasoning is they are not critical in terms of exposure, and they are not reinforced, and also they don't have a formwork where these demolding times or the early age strength development might be critical. Exactly. Yes, these are the three applications. And here also a few project examples. So here you can see how the ULEZ lean concrete was built in at the Zurich airport by Kibak. And then here you have on the left side, it's really the first terrazzo of ULEZ that we tried in our labs. And then this ULEZ terrazzo was built in the Pavillon Manal in Horf as the first screed. It was built in by Repoxit. And we have this development with Müller-Steinach on the pavers that are produced by Müller-Steinach. And when using ULEZ, they can save up to 30% of CO2. Good, so these are the three applications for ULEZ. And what is next is that we are internally working a lot on this reactivity, so to be able to give it this initial boost so that we have a similar strength development curve as conventional binders, and we're working on the development towards a structural concrete. Then we got a grant from the startup from the InnoSwiss for a startup innovation project, where it's about the production scale up of this binder and bringing it to market. And we are working on the certification to get this binder certified. Currently in Switzerland, there is, for binders to be certified, a minimum amount of cement that you still need to introduce into your binder. And ours doesn't have cement clinker in it, so we need to find a way to certify this binder, which would open doors to be able to use it according to the norms. Yes, and then the last project that I want to present is the Pavillon Manal. The Pavillon Manal is a pavilion that was built by Oxara and our partners to display all the construction materials that Oxara developed so far. The building materials were produced by Kibak and TerraBlock, and the construction works were done by Marti and Erne. And we could officially open this pavilion in November last year. That was a nice event. And here we display all the construction materials. So for the foundation, we use the ULEZ, also for the load-bearing columns. In between the columns, we use the NOSIM as separation walls and non-load-bearing walls. And then for the walls, we use the TerraBlock blocks or the Oxa blocks, which are load-bearing, and they're bearing the loads of the roof. Exactly. And now this pavilion is used as an exhibition space for Oxara, but also an exhibition space for the Hochschule Luzern to display architectural projects. And it's also, this pavilion is part of this flagship where it serves as a case study. And of this pavilion, we monitor the durability of the earthen building parts, and that is done by the Hochschule Luzern. And we also monitor the durability of the ULEZ parts, mainly the reinforcement, by Duramon. That is another spin-off of ETH. And in case you're interested to see, feel free to contact us. We are very happy to show this pavilion. Yes, so that was it. Thank you very much for your attention.